Hi everyone. Today, the quantum confinement effect in the MOS system is briefly discussed. Before starting the main discussion, let me explain a way to use a non-uniform grid. This input file shows a two-dimensional PN diode. Its length is 2 micrometer. Here, rectangle supports uniform spacing along each direction. Since ny is 2001, the y-directional length 2 micrometer is divided into 2000 intervals. So the uniform spacing along the y-axis is 1 nanometer. Usually, we wanted to have a fine grid near the junction. However, for a point far away from the junction, maybe 1 nanometer spacing is too small. In a newer version of the G device, another way to generate a rectangular shape is introduced. Instead of specifying nx and ny for uniform grids, we specify the names of grid files. For example, in order to create the same structure, our rectangle part can be rewritten. Of course, we must provide two grid files x.dat and y.dat. The format for a grid file is explained. Currently, we have only two options. Each line of the grid file can have one of the following forms. In the first form, it starts with the number 1. Then the position is specified. In this case, a point is exactly introduced at the position. In the second option, the line starts with the number 3. Then position 0 and position 1 are specified. Also, the number of points is specified. Then, within an interval between position 0 and position 1, points are added. It is noted that the position 0 is not included. For example, when we have 3, 0, 1, 2, it gives two additional points whose positions are 0.5 and 1.0. Again, it is noted that 0 is not included. This file generates the same uniform grid points as before. Now, let's try a non-uniform grid. Near the junction, within 100 nanometer, we keep 1 nanometer spacing, but for other parts, the spacing becomes much larger, 100 nanometer. See this grid file. First, 0 is added. Then, up to 0.9 micrometer, we have 9 points. After that, for 200 nanometer long range, 200 points are added. So, still 1 nanospacing is used. Finally, we have additional 9 points for the remaining 900 nanometer. This figure shows the structure generated by this grid file. Now, we are coming back to our main discussion. In the MOSFET, we have the quasi two-dimensional electron gas. Electronic motion along the vertical direction is prevented by the potential barrier. The electron confined within a short range has discrete energy levels. This is the conduction band energy of the MOS structure. In the left figure, we can see the parabolic potential profile. However, its length scale is 200 nanometer. It is too long to consider any quantum effect. However, as shown in the right figure, within a few nanometer scale, still we have a rectangular potential well. Therefore, we expect that the electrons are mainly concentrated near the interface. Also, due to the potential barrier at the interface, the wave function almost vanishes at the interface. Unfortunately, our simulation result does not consider such an effect. At the interface, the electron density is very high. It is simply because we have not considered the quantum confinement effect. The Poisson equation just calculates the electric field. The electron continuity equation just calculates the motion of electrons. There is no equation for the quantum confinement effect. Therefore, we must consider an additional equation, the density gradient equation. In this equation, the quantum potential is newly introduced as an unknown variable. With this quantity, the electron density at the interface can be correctly described. The density gradient equation should be added to the law. Its reserved type is E quantum potential. When the density gradient equation is added, the integrated charge as a function of the gate voltage is heavily affected. The black curve shows the result without the density gradient equation. It was already shown in the lecture 8. The red curve is the result calculated with the density gradient equation. Effectively, the oxide capacitance seems to be reduced. Why do we have a reduced effective oxide capacitance? This figure compares the electron density along the vertical position. The black curve is the semi-classical result. As already discussed, it has peak density at the interface. When the density gradient equation is solved together, the electron density profile is modified. In the red curve, the electron density shows its peak value at about 1 nanometer away from the interface. Therefore, effectively, from the viewpoint of the gate terminal, the distance to the peak electron density is now increased. The effective oxide thickness becomes larger due to this effect. Of course, when the oxide is very thick, this slight increase will be a minor concern. For a scaled device, it becomes very important. Okay, that's it for this lecture 20. In the next lecture, the gate all-around transistor will be simulated. And the next preview video will be the last one in this semester. Thank you and see you later.